So, today will be the final lecture of module 2, where I will be working on some practice problems. So, in this module you have studied the basics of vectors, vector spaces and vector functions, and we studied some properties of vectors like linear independence and dimensionality, and I will be focusing the practice problems today on these basic concepts of vectors. Okay. And we will look at more problems related to scalar and vector field in the problem sets of the next module. Okay. So, today I will show you some elementary problems that deal with vectors, vector spaces and vector products and the concepts of linear independence. Okay. So, let us take the first problem. So, the first problem asks you, do the following vectors form a basis in 3D space? Okay. So, what do you need to check for a basis? So, the condition, so in 3D space, okay, you can have only 3 basis vectors. Okay. Now, there are many choices for basis vectors, but the conditions for them to be basis vectors is that they should be linearly independent. So, if you have 3 linearly independent vectors, you can choose them as a basis in 3D space. So, what you have to check is whether these vectors are linearly independent. So, R 1 2 1 0 1 1 and 1 0 0, are these vectors linearly independent? Okay, so, that is the question that we have to answer. Now, in general, the way to check linear independence is to take a linear combination of these and set it equal to 0 and see if you get a non-trivial solution. So, what you will say is that you will say C1 times 1 2 1 plus C2 times 0 1 1 plus C3 times 1 0 0 equal to 0. Now, if non-trivial solution exists, that is C1, C2, C3 are not all 0, okay, then the vectors are dependent, okay, or linearly dependent. So, what you have to do is you have to set this condition and you have to check whether there exists a non-trivial solution. Okay. Now, this condition it's actually the way this is actually a set of 3 equations, because this is a vector equation. So, if I write out the 3 equations, so the first equation is C1 plus C2 plus C3, C1 plus 0 C2. So, if you just look at the x component, you have C1 here, you have 0 C2 here and C3 here. So, this should be equal to 0. If you look at the y component, then you have 2 C1 and you have plus C2 plus 0 C3 equal to 0. If you look at the z component, then you have C1 plus C2 plus 0 C3 equal to 0. Okay. So, you have 3 equations and 3 unknowns, okay, and these are what are called homogeneous linear equations. So, the condition for there to be a non-trivial solution of this, okay, that is these equations. So, if I set C1 equal to C2 equal to C3 equal to 0, I will automatically satisfy these equations. But is there a possibility of C1, C2, C3 not all 0? That is what we have to ask. And you might be knowing this, but you can easily show this, that you evaluate this determinant, you look at the coefficients, you put them in the form of a determinant, and so you put 1 0 1 2 1 0 1 1 0, and you calculate this determinant, and it is not hard to show. This determinant is just so it will just be 1 times 2 minus 1. So, equal to 1 times 2 minus 1 equal to 1, not equal to 0. So, since if this determinant is not equal to 0, that means the only solution that exists is for C1, C2, C3 to all be 0. So, vectors are, so that would mean the vectors are linearly independent. And they form a basis. Okay. So, just to recap, what we did was we wanted to check whether these 3 vectors are linearly independent. So, what we did is you write the condition for linear independence, and what you will find is that you will get the condition that this determinant, if it is 0, then the vectors are linearly dependent. If it is not equal to 0, then the vectors are linearly independent. Okay. That means you cannot write one as a linear combination of the others. Okay. And if you cannot write one as a linear combination of the others, then these vectors will form a basis. Okay. And it is fairly straightforward to actually just look at the 3 vectors, and you can immediately see that they are linearly independent, because if you look at the second vector, it has no x component, whereas the third vector has an x component, okay, and it has no y and z component, okay, and the first vector has all 3 components. Okay. So, clearly if you so it is clear that you need what you are checking is whether this vector can be written as a combination of these 2, and just by inspection you can see that that is not possible. Okay. So, this is the problem that has dealt with linear independence. Okay. Now, I will give you another problem, okay, and this is, so the second problem. So, you are asked whether the vectors 0 0 1, 1 0 0, minus 1 minus 1 0 and minus 1 5 49 are linearly independent. Okay. Now, the answer is no, and the reason is that 4 vectors in 3D space cannot be linearly independent. So, if I give you a 3-dimensional space, the maximum number of linearly independent vectors is 3, okay, because the basis of that space is 3. So, you can never have 4 linearly independent vectors in a 3-dimensional space. Okay. So, without any inspection, without checking anything, you can immediately say that these vectors cannot be linearly independent. Okay. Now, the next question has to do with vector spaces and inner product spaces. Okay. So, there are 2 parts. So, first is you have to check whether the set of all square integrable complex functions f of x forms a vector space. I will just put a star in this definition. So, what you have to see is whether the set of square integrable complex functions forms a vector space. Okay. Now, actually this is not a real vector space, this is what is called a complex vector space, but we will just check whether these axioms are satisfied. So, if you want to check whether the set of certain functions forms a vector space, okay, then what you have to do is to check whether given f and g belonging to the vector space V is C1f plus C2g contained in V. Okay. So, if you take any linear combination of this is also contained in the vector space. So, that is essentially the most important condition to check. Okay. Now, a square integrable function in a complex space satisfies So square integrable implies integral f star f dx, and we will just take a one dimensional space. So, from minus infinity to plus infinity, this should be greater than equal to 0 and less than infinity. Okay. Why this should be greater than 0? Because f star f is positive, okay, and if it is less than infinity, then you say that the function is square integrable. Okay. So now let us check whether that forms a vector space. So what you have to do, if you have two functions, okay, that are square integrable, then is a linear combination of them also square integrable. Okay. So what you have to check is whether given f g are square integrable, is C1f plus C2g also square integrable. Okay. So is this also square integrable, and this is what you have to check. Okay. So how do you check this? So you calculate C1f plus C2g, take a complex conjugate, and then you take C1f plus C2g and you do this integral dx from minus infinity to infinity, and you have to check whether this is less than infinity. Okay. So what you will get is that this will be C1 square integral f1 star f dx plus C2 square integral f2 star or g star, it should be g star, f star f, this should be g star g dx. Okay. Now remember, C1 square is C1 star times C1. Okay. So these are the two things. I am not bothering putting the limits here, and then you will have cross terms that will look like C1 C2, or I will write it as C1 star C2 integral f star g dx plus C1 C2 star integral f g star dx. Okay. Now the first two terms are clearly less than infinity. Okay. Since it is square integrable, f star f will be less than infinity, g star g integral of g star g and integral of f star f will both be less than infinity. So the first two terms are clearly less than infinity. What about the third term? So the third term satisfies. So what you notice is that the third and fourth terms are just complex conjugates of each other, and if you take a number and add its complex conjugate, okay, then what you will get is that you will just get the real part of that number. Okay. So I can write this as the real part of C1 star C2 integral f star g dx. Okay. And now actually we will see this in a minute. There is a condition that there is an inequality called the Schwarz inequality, which basically says that integral f star g dx, okay, is less than or equal to. So the absolute value of this is less than or equal to the square root of integral f star f dx times integral g star g dx. Okay. We will show this in the next problem, but the basic idea is that this integral, where you have f star and g, is basically less than the product of f star f and g star g, and under the square root sign. Now, each of f star f and g star g is less than infinity. So, therefore, f star g into integral f star g dx has to be less than infinity. Okay. So, what you get is that this whole thing is less than infinity, because each of these terms are individually less than infinity. So, basically if f and g are square integrable, this is also square integrable. Okay. So, with this you can basically show that this is a valid this forms a vector space. Okay. Now, the next problem is to check whether the inner product defined this way is a valid definition of the inner product. Okay. So, whether the inner product defined this way is a valid definition of the inner product, and again you can show this easily. You can show that if the two condition for validity of inner product is that f times f, an inner product of f with itself. Okay. So, this implies inner product of f with itself should be greater than or equal to 0. Okay. And again you can easily see that. Okay. The other condition is that inner product of f with g should be equal to inner product of g with f. Okay. Now, this is true for a real inner product space. For a complex inner product space, actually this is modified with a star. Okay. These two conditions you can easily see again from this definition of inner product. So, this is a valid inner product. Now, I just want to mention one thing, why I chose this complex vector space. The reason I chose this complex vector space is that this thing is something called a Hilbert space. This space is called a Hilbert space, and this is the vector space in which the entire mathematics of quantum mechanics is performed. So, the entire your entire mathematical aspect of quantum mechanics works on this Hilbert space, which is not quite a real inner product space, but it is a complex inner product space. Okay. Now, the next question. Okay, so just to emphasize, I will just emphasize this here, that Hilbert space is a complex vector space, and inner product satisfies f g equal to g f star. Okay. And f g is given by integral f star g dx, and this is given by integral g star f dx. Okay. So, the Hilbert space is actually this complex vector space where the inner product is defined in this way. Okay. So, and this is essential in quantum mechanics. Okay. So, next practice problem is to prove the Schwarz and triangle inequality for the inner product as given below. So, what is the Schwarz inequality and what is the triangle inequality? Okay, and we will prove this in general. So, I will just tell you what the Schwarz inequality is. So, the Schwarz inequality okay. So, for any inner product, for any inner product space and for any inner product, the Schwarz inequality basically says that if I take an inner product of f g, that should be less than equal to square root of f f and g g. Okay. So, a cross inner product is always less than the product of the individual inner products, the norms, product of the norms. Okay. So, that is the, so in other words I can write this as is less than or equal to norm F into norm G. Okay. So, this is the Schwarz inequality. The triangle inequality, okay, this is like saying that the sum of lengths of two sides of a triangle should be greater than or equal to the length of the third side. Okay. So in terms of vector spaces, so what it says is that F plus G inner product with F plus G, okay, this should be strictly less than or equal to F inner product with F plus G inner product with G. Okay. And yeah, all this should be under the square root. No. In other words, norm of F plus G should be less than or equal to norm of F plus norm of G. Okay. So, this is a triangle inequality, and what we are going to do is we are going to go ahead and show both these inequalities. Okay. Now, there are many ways to prove the Schwarz inequality. The one common method that is used is to actually choose is to use the idea, use norm of any function, norm of any function should be greater than or equal to 0. So in the definition of the inner product, one of the conditions is that norm of any function should be greater than 0. Okay. Then what I will do is I will choose H is equal to F minus G times F comma G divided by G comma G. So, I just took a particular form of H. Okay. And now if you calculate H comma H, okay, you will get it as if you write it out. Okay. So, you will get this inner product with itself. Okay. And what you will get is F minus G F G divided by G G comma F minus G F G by G G. Okay. You can unfold these brackets and you can multiply them term by term. What you will get is H comma H is equal to F comma F minus. So, you will get one term that takes inner product of this with these two terms. Okay. So, if I take the inner product of these two terms, I will have G G and then F G twice. Okay. So, now one of the G G's will cancel. So, I will have F times G into F times G divided by G times G. Okay. And then I'll have two cross terms. So, this multiplied by this. So F times G and then I'll have the same thing here. So, I'll have my okay, this is the plus sign and I have minus 2 F times G F times G divided by G times G. Notice that this particular choice of H ensured that these two terms, the second and third terms, are basically the same. So, what you get is F comma F. So, these two are the same. So, what I get is minus F comma G whole square divided by G comma G, and this because it is a norm of H. So, this should be greater than or equal to 0. Okay. And that immediately implies F comma G whole square should be less than or equal to f comma f times g comma g, and this is Schwarz inequality. Okay. So we have proved the Schwarz inequality. Next we will prove the triangle inequality. So to prove the triangle inequality, you take our, let us look at our expression for the triangle inequality that we had here. So this is the expression for the triangle inequality, square root of f plus g is less than this. Now if I square both sides, okay, then what I will get is the following. So f plus g, so this on the left hand side, and on the right hand side, okay, so we have to check, is this less than or equal to f comma f. So I have the norm of, so if I square the right hand side, I will get this term square plus this term square plus the cross term. Okay. So f star f, so f comma f plus g comma g plus twice square root of f f g g. Okay. And so the question is this less than this? Okay. Now again you can open this. So if you expand the left hand side, you will get f comma f, g comma g, and twice g comma f. So what you have to prove is that is twice f comma g less than or equal to twice square root of f f g g. If this is true, then you satisfy the triangle inequality. Okay. Now clearly f comma g is less than or equal to square root of f comma f times g comma g from Schwarz inequality. Okay, that is just up here. So we just showed this here. So if you just take square root on both sides, you will get exactly this expression. So this implies that this equality holds. Okay, and it implies that this inequality also holds. So therefore this implies triangle inequality holds. Okay. So what we have showed is that the Schwarz inequality and the triangle inequality, they hold for any arbitrary inner product space, and we have restricted to real inner product, but you can do the corresponding for the Hilbert space also. Okay. So I will stop here.